adventure day 2. Hopefully this will go a little bit smoother. It'll be a shorter lesson. I think that will probably help some. So here we go. We're going to be talking about evaluating limits, and this is day 1. So we're going to be breaking evaluating limits into 2 parts. So here's the first part. We're going to be talking about the limits of constant functions. When I have the limit of a constant function, I am just going to be taking my value, and if it's a constant function, my limit's just going to be the constant value. Because if I'm talking about having a constant function, no matter what value I plug in, I'm going to end up with just one value, being that value of the constant. So that's going to be my constant value. But when I have something that has an identity function, notice that I have the limit of x as x approaches c. Notice that that is c. We'll talk a little bit more about that. Notice that the value of x approaching is going to end up being the same thing because it is an identity function, meaning it's just x. So here's a whole bunch of things that you'll find in your book, properties of limits. If I have a property of a sum, if I have the limit of 2 different sums, I can break it up into 2 separate limits. If I have a difference of a quantity, I can break that quantity up into 2 smaller limits, subtracting. If I'm multiplying, I can break it up into taking out the number in front, so the coefficient becomes the number in front of my limit. Same thing if I'm multiplying 2 things, I can break it up and take the limit of 2 different quantities. If I'm dividing, I can break it up and take the limit of the numerator divided by the denominator. I also have a power. I can take the limit of the inside part of my function and take the exponent and put it on the outside. And I also can take a limit of a root and get the same thing. All of those are found in your book, and I think it's a little bit easier if we just apply them as usual, as opposed to just looking at the particular rules. So here's my problem. I'm going to take the limit as x approaches 3 of x squared plus 2x minus 4. The addition property said that I could take it and break it up. So I can take the limit as x approaches 3 of x squared plus the limit of x approaches 3 of 2x minus the limit as x approaches 3 of 4. So basically what I'm going to do is I'm going to take all of those. Notice how I can break up my x squared and take my limit of x and actually square it. And I can take my coefficient and take the coefficient that was in the front and put it in, or that was with the x and was with the front, put it back into the front. So I have just rearranged the problem a little bit until I get to here, where basically what I'm going to do is, if you look back at my equation, I'm going to be taking this 3 and putting it in place of x. And I'm going to put this 3 in place of x. And then this 3 that's over here, I would put in place of x, but there isn't an x. So basically what I'm going to do with that is I'm going to take 3 squared plus 2 times 3 minus 4. And when I do that, I end up with 9 plus 6 minus 4, which gives us the answer that we have here, which is 11. And if I look at the graph, I would see that if I were to look at x, and for my at x of 3, my x value, my y value is 11, which verifies the same thing that we just got by direct substitution. So here's another problem. This time I take the limit as x approaches -1 of 2x squared minus 3 over x plus 2. So the property says that I can break it up and take the limit of the numerator over the limit of the denominator. And then I can break it up some more and just take the limit of each individual piece, which gives me the same thing I have here. But again, it seems kind of redundant to be doing the same thing over and over again, because all we're going to be doing is placing our -1 in place of x. So I'm going to have 2 times -1 squared minus 3, because I can't plug a -1 in for an x because there isn't an x, over -1 plus 2. And then I'm just going to take that and I'm going to simplify it. When I simplify it, I get this, which is -1. So our answer to that equation, yeah, I guess it's an equation. It's kind of more like an expression though, because it doesn't have an equal sign, is just going to be -1, because all we did was a direct substitution wherever we saw an x of replacing what the x approaches in our limit. Here's our next problem. This time I have a square root. So I'm going to be putting a 2 in place of x. wherever I see an x in my equation, and then just simplifying. So when I do that, I'm going to replace this x with a 2. And when I do that, I get the square root of 2 plus 4, otherwise known as the square root of 6. And that's my limit. It's as easy as that. This just says that if I am taking the limit of a polynomial, all I'm doing is finding the value of the polynomial by putting in what the limit approaches. So since the limit approaches c, I'm just going to substitute c in. And the same thing for the limit of rational functions. Then for this one, I'm going to use direct substitution. I am going to place positive 2 in place of x. So basically, since it's a polynomial and I'm not going to have a 0 in the denominator and I'm not going to have an imaginary number, that means it's going to be possible. So if not possible, in this case, really doesn't apply. That only applies to a fraction, making something that's undefined or undefined in the denominator, or if I had a number that would make it like a square root of a negative number. So all I'm going to do is I'm going to place the 2 in for x wherever I see it, which is what I have down here. And then I'm just going to do the math. And when I do the math, I end up with -3. So the limit of all of this stuff ends up to just be -3. Now I have this problem where I'm going to, again, use direct substitution if possible. So I'm going to put the -3 in for x. If I put the -3 in for this x here, I can see that -3 minus 2 is -5. That's okay because I don't get a 0 in the denominator. So that means I can go ahead and stick the 3, substitute technically, the 3 in for x and find out what I get. So if I do that, I would put the -3 in place of x. It's kind of hard to see that -3 in that part there, but it's a -3. I'm going to put a -3 in there, and I'm going to get -3 squared plus 1 over -3 minus 2, which if I do the math, I just end up with 10 over -5, which is in fact -2. So that's my limit. And again, if I were to graph any of these, I would still see that if I look at the x value of -3, my y value should be -2. Here's another one. I'm going to take -4 and I'm going to put it in place of x. So if I put a -4 in place of x, we have a problem because -4 plus 3 gives me -1. So if I take the square root of -1, that means it's imaginary. So that means it's not possible to do a direct substitution. So that means it's not a real number. So that means my limit does not exist. That's what happens when you have a negative inside a radical. Now in this problem, if I look, I'm going to put 3 in place of x. So if I put 3 in place of x, oh geez, we have a 3 in the denominator, which tells me right away that that's going to be a bad thing. But if I put the 3 in the numerator, I also get 0. So whenever you get 0 over 0, which is what I have here, that is called in calculus indeterminate form. Indeterminate form. So indeterminate form tells me when I have 0 over 0 that that's a problem and we need to do something to try to fix that. So what we're going to do is, hey, why don't we try factoring? So that's exactly what we're going to try. We're going to factor the numerator. So if I factor the numerator, I get x plus 2 over x minus 3. Hey, look at that. When I do that, and this is usually what happens, I notice that I have x minus 3 over x minus 3, and those cancel out. When I do that, notice I'm just left with x minus 2. So since I'm left with just x minus 2, I can do my direct substitution. So when I do my direct substitution, I get 3 plus 2. So that tells me my limit is 5. Most of the time when I do these, I'll notice that they will, when I factor them, they do cancel out. And that's what I want. Usually if I can't cancel it out, that's a problem. So make sure you double check your factoring if that doesn't work. So just go back and double check that. Oh, there's our answer if I do my direct substitution, which gives me just 5, like we said. So here's my next problem. If I plug in a -2, I should see that, again, I end up with 0 over 0. So that tells me indeterminate form. Once I see that I have indeterminate form, that tells me I need to try to factor. So I go back and I look at the top part of that problem. I've got 4 terms and I have to factor it. Gee, I wonder what I'll have to do. Oh, that's right. I'm going to have to factor by grouping. Yay! So I'm going to go and factor it. And when I do, I end up with x squared minus 3 over x plus 2. Lucky for us, the x plus 2 cancels out from the top and the bottom. So I'm left with 1 over x squared minus 3. So then I have my negative 2. I can plug my negative 2 in for x. When I do that, I'm still okay because I end up with just 1. So that means that the limit of all of that stuff is just 1. So the moral of the story is, if you have something that has a limit that you're finding, you can do a direct substitution and just stick that number that the x is approaching in for x, unless you get indeterminate form, which is 0 over 0 in a fraction, which tells you need to factor, or if you get a negative inside a square root, which tells us that we're going to have an imaginary number, which tells us the limit does not exist. We'll talk more about a couple other indeterminate forms and other ways that we can solve that in part 2 of this. So good luck, and let me know if you have any questions.